Hi, so my name is Sheng. I'm from Rancher Labs, and today we'll be talking about how we build a Kubernetes-based cloud-native storage software from scratch. So many of you may have heard about Rancher Labs because of Rancher or K3S recently, but there's another project we have been working on for the last 4.5 years. That is starting since the starting of the Rancher company. So that is Project Longhorn. So Longhorn is an open source distributed block storage software for Kubernetes. You can find more information about Longhorn in the GitHub links now. And what Longhorn do is with a very easy way to add persistent storage support to any Kubernetes cluster, no matter where the cluster is being hosted. So you can add the Longhorn to your system just using this one line of kubectl command. But many people will raise questions. There's already so many existing storage solutions there. Why we need Longhorn? Let's compare Longhorn to the legacy storage softwares. So normally, the legacy storage softwares implement sophisticated storage stack that's including disk management, storage visualization, file system, and the storage protocols. And many of them may be proprietary. And also, they have H8 as storage controller that handles very high I/O ops and throughput across the cluster, which can be a bottleneck in the real use. And last, most storage systems are built upon the hundreds of thousands of lines of code, or if not more, and it's very complex. So the approach we take with Longhorn is different. We leverage the modern high-speed, high-capacity SSD and NVMe, and we use proven Linux storage features like sparse file and C groups. And we are using each volume in Longhorn is a set of independent microservices, and we utilize in Kubernetes and other existing technology to orchestrate that. That's reduced the complexity in the Longhorn itself. In the end, Longhorn only currently have about 30,000 lines of code. We're writing mostly in Go and broken into clear pieces. You can easily read the code and understand it and work with it. So in the end, Longhorn is a microservice-based, Kubernetes-based storage solution. So our latest release is Longhorn 0.5.0, and currently Longhorn is still in the alpha stage. And as I said, Longhorn provides enterprise-grade distributed block storage software for Kubernetes, and we support volume snapshot, backup, and restore. The difference between the snapshot and the backup is the snapshot was taken inside your Kubernetes cluster, so data doesn't leave your cluster. But the backup is the way we provide a way to migrate, you back up your data into someone else, like AWS S3 or any S3 compatible object stores or the NFS server. So in that way, you have another fail-safe for if anything goes wrong with your cluster. One of the highlighted features we have with Longhorn is we support live upgrade of Longhorn software without impacting the running volumes. I will demonstrate that later. And we also support cross-cluster disaster recovery volume with user-defined RTO and RPO. Many users like Longhorn at first sight because Longhorn has a very intuitive UI. So we provide an UI as a complement of the function of the Kubernetes, like besides the create and delete volumes and snapshot, UI provides the full functionality like a backup and other operations for your Longhorn systems. And we support one-click installation, as we mentioned before. You can use kubectl, apply a YAML file, or you can use a Helm chart, or you can use Rancher catalog apps to install Longhorn with zero configuration. Of course, more features are coming. We are planning to do the QoS, volume resizing, and real-time performance monitoring, etc. So that's to talk about a little bit about Longhorn's architecture. There's two main components of Longhorn. the engine, which handles the data plane, implements the block device, which is used by the user. Another part is manager, which orchestrates the engine across the cluster. Let's look at the engine first. So here, we have 2 nodes as an example. Each node has some hard drives, and RAM, and CPU, and memory. So when Kubernetes create a pod which requires a persistent volume, Longhorn receives that request, and will create 2 replicas on 2 different nodes, and probably different disks, as long as that disk has enough space to accommodate the volume. After we create the 2 replicas, we create an engine which connects the 2 replicas and implement the block device, which will be mounted, will be attached to the same node as the pod is running. And then Kubernetes take the block device, format it, and mount it on the host namespace, and then finally bi-mount it as the volume inside the pod. So the reason why we separate 2 replicas is because if one node goes down, we still have 1 replica running, and as long as the volume has 1 replica exists and running, the volume will be fine. So what will happen if you have multiple pods? As you can imagine, the same things happens. Very simple. We create 2 more replicas and 1 more engine for the second volume and the third one. So in fact, this approach has a very desirable effect that the data path of each volume is isolated from each other. As you see that, if one volume goes down due to whatever reason, there's no reason for other volume to be affected as well, because the data path is completely separate, it's not interact with each other. But now we have a question. How can we manage all these engines and replicas? So they're managed by the Kubernetes. So that's the answer. We are utilizing Kubernetes to manage all these moving parts, and we cannot do that without Kubernetes. Because in the past, there's no Docker container technology, there's no Kubernetes. It's pretty hard for us to do the microservice in this level. So we built the Longhorn Manager based on the Kubernetes. Here's the architecture of the Longhorn Manager. Still assume we create a new pod, we want some volumes. Kubernetes is going to talk with the Longhorn CSI plugin. CSI is the container storage interface. I think Start has mentioned that in his keynote, and it's a very convenient way for the storage vendor to hook into the Kubernetes. And the Longhorn CSI plugin will talk to the Longhorn Manager through the Longhorn API. In fact, the Longhorn Manager is just like another controller inside Kubernetes. The Longhorn Manager will create new CRD object, customer resource definition object inside Kubernetes API server, so we don't have the burden to have another data store. So the change of, say, Longhorn Manager create a new volume CRD inside the Kubernetes API server. That one will be picked up by the other controllers, the volume controller inside the Longhorn Manager, and that controller see that, okay, now I have a new volume, so I need to create a new engine and replicas to implement that volume for the user. If you have multiple requests, they see the same. So the Longhorn Manager is implemented on top of the Kubernetes cluster to do all this kind of orchestration works. Another way to interact with Longhorn Manager is using the Longhorn UI, as I mentioned before. So Longhorn UI provides backup and live upgrade, cross-cluster, disaster recovery, these kind of features, in addition to Kubernetes provide create, delete volume, and the snapshot if you have external snapshot plugins. So that's about Longhorn Manager. So this is really getting interesting. If you haven't know about what is the controller pattern or operator pattern inside Kubernetes, I can show you an example here. So on the right, you can see that we have a volume object, we have one engine object. Each of them have 2 fields. One is called spec, another one is called status. So basic concept of controller pattern is we are always working towards reconciliation these 2 states. And we are going to check what our current status is and try to reconcile that with our spec to reach our desired state. Let's take an example that how Longhorn handling the self-healing. Say I have 3 replicas on 3 nodes and 1 engine talking to all of them, and the engine constantly talks to the manager. Now, suddenly, node 3 is down. Longhorn engine will detect that immediately and mark the replica 3 as red, as arrow in the engine status field. And that information was going to be picked up immediately by the manager. So manager found, OK, there's a bad replica. I'm going to remove it. The manager removed the replica 3 for the engine spec, so engines know that I don't need this replica no more, so I just disconnect it totally. But as you notice, the number of current healthy replicas in the volume status has been reduced to 2 because we lost 1 healthy replica. So manager decided that, yes, we see that there's a 1 replica difference between what we have right now and what we desired. So we're going to create another replica. The manager found another node, node 4, which is available, and the space is suitable, so they create a replica 4 on the node 4. And after the replica 4 gets started up, the replica 4 manager will add replica 4 in the engine's spec, and the engine will receive the spec, say, OK, so I'm supposed to have replica 4, but I don't have now, so I'm going to add replica 4 in my status. And that engine is going to connect to replica 4 and start a process we call the rebuilding. The rebuilding process is basically copy the data from existing healthy replicas to the new replicas and to make sure that we have the correct resiliency of our volumes. Once rebuilding is done, the replica 4 will be marked as green, and you see the current healthy replica count on top right will update to 3, and this fits our spec. So that's the whole process of how the Longhorn self-healing process was driven by the controller pattern based on the Kubernetes. All right, so yeah, let's do a live demo now. This will going to be a little bit risky, so if anything goes wrong, please be kind. All right. OK, so what I'm looking right now is Rancher, our Kubernetes management platform. And I have a demo cluster setting up here. I'm going to currently, this is the storage project. Project is the concept of Rancher, which is just a bunch of namespace, nothing fancy. And we are going to deploy Longhorn using the Rancher apps. So here is the Longhorn catalog in the Rancher apps, and you can just click View Details, and then you can start in. But now I'm going to demonstrate how live upgrade works later, so I'm going to choose a slightly older version. I want this one to name it as the Longhorn system. Let's click Launch. So the app is also a way to aggregate all the related components like a different deployment, different services into one catalog. As you can see that we have 3 major workloads here. Longhorn Manager has been deployed, and the Longhorn UI, as I mentioned, going to talk to the manager. Another one here is the driver deployer. I will explain what they do later. All right, so there's one advantage of using catalog apps is if anything is supposed to be upgradable, you will see that directly. But we're not doing that now. OK, so now you're seeing is what the Longhorn's dashboard looks like. 3 parts, very clear. The left one, do we have any volume now, the volume state. The middle one, how many we have remaining in our storage. The right one, what's the node status. And the Longhorn gets node status directly from the Kubernetes node object. And also here, we have a bunch of event log. which is we basically use the Kubernetes event log and to record what's happened in the Longhorn as well. So we just set a different source so we can filter it down. But basically, this thing is work on the Kubernetes. So let's take to a node. As you see here, by default, we have a path which we going to use as to store the data in the replicas. And for each node, you have add more disk to it through this way, or disable it, or doing something like, say, disable scheduling for the node or disable scheduling for the disk. And okay, you can also say that how many volumes has been allocated in this node. It's basically the space taken by the replicas, and what is the real-time usage of this disk and this node, and what's the total size of this disk. The next tab is the volume, which we don't have any run, so I'm going to skip that for now. The next one, okay, you see the arrow here. Why? This one is the backup. So in order you have the backup, as I mentioned, it's basically a defined place you can back up your snapshot to, but you need to define that place first. So let's go to the settings and set a backup target. So basically what I'm doing right now is that I have a Minion which is installed inside this Kubernetes cluster and acting as S3 for us. And now the backup error information is gone. And now let's deploy some workload on that. All right, so for example, I'm going to use WordPress. So I choose the WordPress from the Rancher catalog. And I want to set the WordPress password. And enable the persistent volume using Longhorn. I want to do the same for MariaDB as well. OK. So let's take a look back at the Longhorn dashboard. So now the WordPress application has been installed. It's being installed. So the Longhorn should have a very, see. So WordPress, as I said before, requires 2 volumes. And the WordPress is creating that inside. Longhorn received that request and creating volumes. And you can see that this color means that we're in progress. It's either creating, attaching, or detaching. And if you take a volume page now, you can see that 2 volume has been attached. The health is healthy, and it shows some information about volume as well. Let's take a look back at the WordPress. OK, so the MariaDB is up, but it hasn't been completed yet. Let's take a look at log. OK, now I think it's going to be up very soon. Yeah. You see MariaDB is running. So the WordPress, it depends on MariaDB, so you have to MariaDB has to run first. OK, I think, yeah, the WordPress will be running soon. Yeah, I think that's it. All right, let's take a look back at the apps. Now the apps provide a very convenient interface to access any service. And now the WordPress is up. Let's write something to it. Hopefully you get it right. Yes. All right, let's add a post, say, KubeCon demo. Longhorn works. Not very exciting, though. OK, so now this data has been written into the Longhorn system. And now I'm going to try what I mentioned before, a live upgrade. The first part that will be, I just clicked upgrade here. I'm going to this one will upgrade the Longhorn manager. And just click upgrade. All right, I guess I need to refresh the page. And during this time, of course, the WordPress still working, no problem. You can click, you can add comments. No interruption. And here, yes, yeah. You see that the image has been reflected into the new image, and the manager is almost done with upgrading. And let's take a look at the UI. OK, not done yet. Let's try again. So of course, when you upgrade the Longhorn manager, the UI service will be interrupted. Probably I want to do this. OK, now it's back. Now you can see that the version number has been changed to 0.5.0. And the next step, we're going to do an upgrade. You can see that because the Longhorn manager is different from it's the orchestration level, and Longhorn engine is the one provide the data path. So let's do an upgrade on the engine. This is far more risky than what I did before, but let's try it if it works. OK, let's go have engine upgraded. They're doing that right now. Turns out WordPress needs to upgrade as well, so I click this one. These two processes happens simultaneously. WordPress finished pretty fast, but I guess they have a bug. Yeah, it's supposed to be 5.2.1. And let's take a look at the engine. Yeah, the engine works now. Because you see that the green arrow in the front is gone, and you can see that yeah, the engine version has been upgraded to the latest one. So now you are looking at is the volume detail page. So it gives you every detail of this volume. You can see that where the replica resides at, what node is running on, and even what's the location of the database stored on that node. So you can take a snapshot or create backup easily. Another feature we have is we have a recurring snapshot and backup schedule, which means that you can decide that when would you want to take snapshot and a backup during, say, low traffic hours, like 3 in the morning. Let's try that. Yeah, in fact, I don't have that much time, so I just take a backup every minute. I want to return the last 5 of them and save. So can you guess how we implement this feature? OK, it's done by using the Kubernetes cron job. It's 100% just cron job. All right. So now you can see that this now the scheduling has been scheduled. And you can see the last backup is created. OK, it was minutes ago. Now it's a few seconds ago means another backup is still going on. And also, now in the new version, you can see that you will have more information presented in this dashboard. You know who the PV, who the PVC is, and what namespace they are on, and what pod they are using the volume. This is one purely based on the user's feedback that because the Kubernetes provide the storage vendor only a very random PVC name, they have no way to associate that volume with the actual workload. So we added the feature, make it easier for the user. All right, so I guess that is the demo. That's the end of the demo. Let's go back to the slide. Yeah, in fact, let me refresh this. Oh, that's one other step. OK, now it's done. Sorry, one moment. Yeah. So like I just demonstrated, Kubernetes orchestrates the data plane because the engine pod and the replica pod are scheduled to the associated nodes by the Kubernetes. And also, as you see, each replica contains a full copy of the volume, and you can see easily where that data resides on your node. So that means only one correct replica is all that need if you really have where disaster happens and try to recover your whole volume. That is very transparent compared to many other storage vendors' approach, which they just have a block present to you, but you don't really know where the data is that or not. Also, Kubernetes helped to increase resiliency, like what I mentioned. The node status was we got from Kubernetes. So if any node is down, we are going to skip that node for the scheduling and do some failover recoveries. But in fact, the core logic of the data plan not really rely on that, depends on that, because Kubernetes is kind of slow and reflecting what the pod status is. So the engine itself will decide if a replica is bad purely based on its connection to the replica. So that makes it very faster. And the pod status monitoring, yeah, we still rely on, we get some information for the Kubernetes if something goes wrong. And we automatically connect log if something unexpectedly happens to that replica or engine pod. Another feature is we can automatically retach the volume. If you reboot your Kubernetes boot node, we use a special field called boot ID inside the Kubernetes node object. That ID will be refreshed every time when you reboot a node. So we use that to decide if this has been rebooted or not. Of course, there's always a few issues when you're working with Kubernetes. Well, I don't know if everybody agrees. But at least as a storage vendor, there's two major things we had. The first one is the driver interface, in fact, is keeping changing for almost every other major version. Before, the Kubernetes has a standard called Flex Volume, which they think probably not going to the GA, but in the end, it's went to the GA and become one of the standard. And since 1.11, the CSI 0.3 was out and is in the beta, so we started using CSI. And then we found the CSI 0.4, which is 1.12, breaks the compatibility of CSI 0.3. And the CSI 1.0 into 1.13, yeah, breaks backwards compatibility again. So the Longhorn adapts by using one small tool we call the driver deployer, as I showed you before. That's one will automatically detect what the environment is, what your Kubernetes settings, what your Kubernetes version to decide what's the proper way to deploy your driver and what's the correct configuration for that. Another issue is related to the controller pattern we are using. So if you have been familiar with the Kubernetes controller, you know that we're normally using something called informer and lister. And the informer contains another object called the lister, which is easily used to access the Kubernetes CRD objects in the cache. That's why it's much faster than using the API directly. But we found out the lister can sometimes return the stale information even with one node. So here's some example. The correct sequence is something like this. Client issue a request to the API server, create a new object. API server using the etcd watch mechanism, tell the lister, yeah, now you need to update your internal cache. And the object will in the cache, and the client will go to the lister to say, OK, what's my new object? It's there. And this one is correct. But sometimes, the race condition happens. The first step is the same. Client issue a new request to create a new object. But before API server notify the lister to update its internal cache, client make the query for the new object. Of course, object is not there. The problem is the process of client issue a request and the lister updating internal cache is asynchronous process. They're not really sequentially, so the client will see this kind of strange result. I create object, but it's not there. I update the object, but the change is not there. So Longhorn have to implement additional levels of cache validation. Basically means that whenever we do a modification to an object, we need to wait for the lister to return us a newer version. You can check that by using the reverse version inside that object. As long as after we can confirm that lister returns us a newer version, we cannot continue. All right, so the upcoming Longhorn release will be 0.6.0. It will be the one we announced beta. And yeah, we need to go do some re-architecture there on the engine level. The engines and replicas will be run and processed inside the daemon set pod instead of each pod for each engine and replica now. that gives us a few better results than the current solution. So we should be able to speed up the volume attach and detach process, because whenever you start, even though the container and the pod starts and stops very fast, it's not as fast as you start and stop the process. Another one is pretty major, because Kubernetes has a pod limitation of 110. So basically means that you can only have 110 pods per node. And we already have some users hitting that, because we're using pretty much many pods per volume. So we're going to avoid that by running just a daemon set pod on each node. And the third reason is now we can get guaranteed the CPU resources for the daemon set pod. Before, we can really not do that, because the Kubernetes scheduling doesn't know about the storage, and the Longhorn scheduler doesn't really know about the CPU. So now we are basically, the daemon set pod, we can set the CPU guaranteed on that and make sure that the other process in the same node will not really eat into the engine's CPU cycle and make it delay its response, because as you know that the time is really sensitive on the block storage. So that concludes my session. Please check out Longhorn. And we are going to have a website up soon and at longhorn.io. We're still working on that. And I also want to thank you, the users of the existing Longhorns, because we're still in the alpha project. But many users give us many feedback regarding how they want to see this project going, what feature they want, and some of them even give us live environment to debug some tricky bugs. I really appreciate for that. So if you haven't, please check out Longhorn. Thank you.
Please remember to give the talk a rating on the schedule, and we have time for a couple audience questions before lunch.
Hello, thank you for your talk.
Yeah.
What's the position of Longhorn against Rooks? Does it intend to replace it or to be integrated?
Oh, OK. So yeah, everybody know about Rooks. Rooks is positioned to be a storage operator. It's not really a full stack storage solution. Rooks rely on the Ceph. And because I worked for Cloud.com and other companies before, we know that Ceph, there's many users complain Ceph is way too complex. It's very hard to maintain. You sometimes don't know where your blocks is, and sometimes you probably configure your crash map wrong. So we're not looking to replace Rook, but at least we want to provide an alternative to the Ceph as a simple and more usable, more user-friendly solutions.
Can you maybe explain a little bit more about the internals?
Sorry?
Can you explain more about the internals? What SCSI do you use? I read something about you need to install some tools.
Oh, OK. All right. So in fact, I have backup just for that. So in fact, we have tried a few ways to expose the block device, and we tried the NBD, which is very easy, but not reliable at all. It's easily cause a kernel crash. And we try to use the TCMU and spend quite effort to that. And I contribute to a few kernel patches to TCMU to increase the performance. But in the end, we found the limitation that because it's kernel, so it's really take a long time to get down to the end users. So I don't want to limit it out the user because that we require TCMU. And also, we tried Fuse. Well, it's too slow. And in the end, the block device, we are using the TGTD and iSCSI combination. The TGTD is a kind of very old iSCSI user space framework, but it's very stable. I didn't see it crash the kernel anytime at all. And the process is most likely it will get a little bit complicated here. But basically, the engine will start a TGT target inside the container, and then engine will talk to the host and using the iSCSI admin on the host to connect to that TGT target. The reason is iSCSI D, which is open iSCSI, is not really namespaced. The kernel has they need some kernel patch to support that. That haven't happened yet. So you can only have one iSCSI running in one node, and the Ubuntu and other major server distribution already supports that. So I don't want to have our own installation and probably potentially disrupt others. So after we got into the node and using iSCSI admin to create the block device, and then you can mount it and use it in the user pod. So that is how we implement the block device part.
All right, I think we have time for one more.
Hi, thanks for your call. Do you respect data locality? So, so one pod is writing to the disk and using only the local disk on the local machine and not doing the writes?
No, in fact, in Longhorn, every replica is treated the same. So we're not really prioritize anyone. Basically, when you do a write, you write to the old replica simultaneously. When you do a read, we basically employ a round-robin mechanism that you just read another replicas, and whatever replica is in read-write position, we can read from it. Yeah.
Bonus, can you evict nodes?
Sorry?
Can you evict nodes, so remove it from the cluster and all?
Oh yeah, sure. You can remove it from the cluster, yeah, because after you remove, it's basically just the worst case scenario is one replica is gone. And then as I demonstrate on that controller pattern slide, we're going to rebuild a replica for another node, so the volume will stay healthy.